Okay, I think we can formally start because the time is now. Um, uh, Welcome everyone. Welcome to the session, XC2 demo session of machine learning for and with software engineering. So actually, it's been very topic research direction. Today we'll be having three presentations. The first one will be Hoot, a tool to debug DNNs for safety analysis. So Fabrizio, so please go ahead with your presentation.
Okay, hello everyone. Can you see my slides?
Yes, I can see that.
Yes.
Okay, perfect. So this is our tool to support DNN analysis and retraining. And this is a joint work done with Hazem, Mojtaba, and Lionel Briand. And basically, the motivation for our work lie on the requirements of current standards. And as you may know, safety analysis standards targeting autonomous systems like the SOTIF standards still recommend to rely on accuracy evaluations using inputs from simulators or data from the field to evaluate the DNN in a traditional manner with the approach that I show below. And this is considered useful because then you rely on the manual inspection of the images that lead to DNN errors for root cause analysis, so to understand what is the reason why the DNN does not perform well. And this is useful to identify the unsafe scenarios and then improve the system, and to demonstrate that unsafe scenarios are unlikely, for example, if you have a high accuracy. However, there are still open problems with this approach suggested by the standards because the manual inspection of these error-inducing inputs is error-prone and expensive, and the manual identification of additional inputs is expensive. Furthermore, underrepresented unsafe scenarios may remain unnoticed, and an unsafe system might be released. And this is particularly dangerous for the developers of components that needs to be installed on car. For example, a sensing system that is based on computer vision that you can, use inside the car to track the people who are in the car. Because even if you have a high accuracy, those developers are still considered liable for, any mistake, any error in the field. Therefore, we need to improve this situation. We have some tools, for example, for DNN explanation, but they tend to boil down to generating heat maps. So an heat map basically captures the extent to which the pixel of an image impact on the DNN result. For example, it can show that long hair is what caused a female doctor to be classified as a nurse. But it still has a limitation. They need to be inspected manually, which is expensive. And again, underrepresented failure causes can remain unnoticed. And also, it does not help automated retraining, automated improving of the DNN. So we end up with a solution, a technique, and a tool that I will show today that basically rely on heat maps to generate cluster of images leading to a failure because of a same root cause. So basically, a root cause is a common characteristic of the images that impact on the DNN result. And these images are inspected by the engineers. And they enable engineers to ensure safety, for example, by introducing countermeasures. Maybe the engineer may realize that, he needs to introduce an additional camera, or they need to introduce also not only vision, but also radar system. This is, what they need to perform for safety analysis. And then we also automatically retrain the DNN by selecting new unsafe images belonging to the identified clusters. And this helps removing root causes identified with a reduced cost. I briefly go through the different steps. So first, we perform this heat map-based clustering. So we rely on we start from these error-inducing images, and we rely on the layer-wise relevance propagation approach to generate heat maps. And then we can compute the distance between the heat maps of the different images. We generate heat maps for each layer of the DNN. And then for each layer, we apply a clustering algorithms to end up with clusters of different images. Then we identify the optimal clustering layer, which is the one with the most cohesive clusters. And these are basically our root cause clusters. These root cause clusters include different number of images, and a few images should be inspected by the engineers to understand, what is the common cause of the error. For example, they may realize that there is a cluster representing borderline cases, one representing infrequent cases, and one incomplete requirements analysis. Then, to improve the DNN, what we do is that we require an improvement set of images that does not need to be labeled. Then we automatically identify unsafe images, which are images that are close to the ones belonging to the clusters that we generated before. And you can see here example of images that we select as being similar to the ones in the Claude root cause cluster. They have, for example, the same position. And then we ask engineers to label images, for example, because if we come with an improvement set of images that is unlabeled, we select a subset of them and we ask engineers to label them. And this is a big saving in the cost. Instead, if the images were provided with a simulator which has labels, our approach is still useful because basically what we have observed is that the images selected by our approach provide better results than images that simply lead to a DNN failures. So once we have identified these images which are then labeled, we perform bootstrap resampling to give to each cluster the same likelihood of being improved, and then we use them for retraining the DNN. Just before the demo, I just tell you that we have an empirical evaluation that is described in a journal paper with the approach. We consider case studies that are, related to car sensing. And for example, we evaluated if they had enabled engineers to identify the root causes of DNN errors. For these, we have considered images generated with simulators. And we have seen that a very high percentage of the cluster include at least one parameter with 50% reduction in variance, which means that engineer can likely identify the commonalities among images. Also, we have seen that all these parameters are likely related to characteristics that are plausible causes of DNN errors. Also, we compared the approach with baseline approaches for DNN improvement, and which is basically retraining the DNN using images that lead to DNN failures or using with random images. And we compared them with the accuracy results obtained with our approach. And basically what we observed is that our approach always achieve a better gain, a better improvement delta, a better delta in the improvement of the accuracy, even when there is little room for improvement. Now, this is the approach which we implemented in a tool. This is the architecture. We have an entry point that we call helper that invokes different modules that perform the analysis, and I'm going to show a screencast demo of the tool. So let me just change the sharing settings. So this is the video of the tool that you should see, and we start by configuring the tool. You can see the video, right?
Yes, we
can see. So
you
can see that here we configure some parameters, for example, the type of DNN under the analysis, the AlexNet. And then after configuring the tool, what we need is to have information about the result of your DNN. So we need to know which are the inputs that lead to DNN failures. We have a module that helps you collecting this information that invokes this test, that is invoked by this test model command, and it collects the information that is stored in some CSV file. For example, here you can see that the accuracy of the training set is 94%. The next step is to generate heat maps. Heat maps are generated for each input leading to a DNN error. And we can see here, for example, that we are going to generate 1,500 images, and they are stored. So the heat maps are stored for each layer. We generate one heat map, and for each image. These heat maps are very important because they contain information about what is important for the DNN to generate the result. And they are, of course, different for different images. Then the next step is the clustering, and the clustering is performed with these generate cluster commands that basically first start computing the distances between the different heat maps. They are stored in a file that here it is shown in the top right, and then after we generate these heat map distances file, we start generating the clusters. The clusters are generated with the hierarchical agglomerative approach with word linkage, and then they are stored. I show here what we generate as a result. First of all, we generate as a result this heat map matrix that, of course, the end user doesn't need to inspect, but for example, it can be used by other tools to build on what we generate. Here we see that the distance between the first and the second image is 1.6. But then the important information that is processed by the end users are the clusters themselves. For the clusters, basically, we expect each user to inspect a few representative images for the cluster. But also what we generate is an animated GIF with all the images belonging to a cluster, so that basically what you can do as an end user, you just can look at a sort of video with all the images belonging to a cluster to understand what is the commonality. Understanding the commonality is useful because it helps the engineers to decide how to improve the DNN. Okay, for example, by just retraining the DNN, increasing the training set, or adding or changing the DNN architecture. I'm going to show now a few examples of these clusters. For example, here we can see a cluster with borderline cases. Basically, all the images are looking between middle left and top left in a system, and the DNN here was classifying the gates direction, okay, between top left, top right, and so on. And here, basically, what the engineers should have done to improve the DNN, for example, is to add additional images with these characteristics, and this help retraining the DNN and improve it. Actually, this type of improvement is what it is automated by the next step of our approach. What we have here is another cluster, and this is a cluster with a sort of infrequent cases. You can see that the person is looking top right, but the eyes are looking in an opposite direction. So what you can do as an engineer is, for example, collect additional images strange like this, or configure your simulator, in case you are using simulator to generate images, to represent those situations. Here we have another case instead of another cluster, and this is a cluster where you can see is for another case studies where we were classifying the gaze direction of a single eye, and you see that all the eyes are looking in the same direction, middle center. You can also see how it is easy to understand what is the common characteristic by just looking at this video. And in this case, the problem was that we forgot to add to the DNN a class representing the case in which the eye is looking middle center. Then the next step is simply to perform DNN retraining. DNN retraining is performed, as I told you before, by considering a big set of images that are not labeled, by selecting the ones that are interesting among them, that we call them the unsafe set of improvement images. And then after we select them, our approach performs bootstrap sampling to give the different cluster the same likelihood of being improved, and then we rely on those images to perform the retraining. Now, what I'm going to show you is examples of the images from this improvement set, which are images that were never considered neither for training nor for the testing of the DNN, how we assign these images to the clusters, because they are useful, let's say, to improve the DNN for the different cluster. Here we see the command that is used to assign the different images to the different cluster, and then you can also inspect how the images are assigned. For example, here I open on the left a set of images that are assigned to a given cluster. And the cluster here is represented by the images on the right. And you can see that most of the images are looking in the same direction. So actually, they are really similar with each other. The last step is just to retrain the DNN. You can do it manually, or we provide a utility that basically takes the images that we selected before and retrain the DNN. And then the DNN is stored in a specific folder. So this concludes my presentation. We have a dataset and the tool available, and we will also release soon the source code of the tool. Now I am available for questions.
Okay, thank you. Thank you very much for the presentation and the demo. Yep, very wonderful tool. But I don't think we can have we cannot ask you the authors to answer the question now. But you can still use the chat box. Can you see the question in chat box? And I think you can answer that. And for other participants, you can type your question in the chat box, and the authors should give you can give you their answer in the chat box, and we won't use the live discussion, okay, because we're running out of time. We should shift to the second presentation. And thank you very much. A wonderful, a very nice job. Yeah. Okay. The second, Weixiang, you can start sharing your screen. The second presentation will be given by Weixiang Yan, and the title is YGen explaining ML powered code generation by referring to training examples. So please go ahead.
Hello, can you hear me?
Yes, I can hear you.
Okay. Hello, I'm very happy to do this presentation. I'm Weixiang Yan. I'm glad to introduce YGen, tool to explain deep neural networks model generated code by referring to the training examples. Let's take a look at machine learning powered code generators, that is Copilot, launched by GitHub not long ago, and run an interesting test on it. First, we input some annotation to see what result Copilot will generate for us. It really produces a perfect, correct result, but the code is copied uncharged from the web, which will cause some problems. Now let's take a look at what problems deep learning code generators may cause. If the training examples are highly imitated or recited, it will damage the copyright of the code. In addition, high imitation or recitation may reveal some personal information in the source code, which has already happened on Copilot. It can be seen that many developers have expressed strong dissatisfaction about the Copilot's illegal recitation and other problems. Therefore, we hope to solve the above problems through the technical methods. Next, I will introduce our approach YGen. YGen explains the generated code by referring the related training examples. Specifically, if the code generator generates a code that is recited directly or highly imitated from the training samples, YGen will inform the developer, as well as the source and the number of times the code appeared in the training examples, so the developer to decide whether to use the code provided by the code generator. In addition to this, the developers can learn more about by looking at and how the code is originally used, and the original authors of the code generator can get credit. Let's look at a case demonstration of YGen. As can be seen from the example, when we enter some code as the query code, the code generator generates the next line of code. At this time, Ygen returns the top 5 training samples, the most relevant to the generated codes in the training set, and their source path in real time. Ygen looks interesting, so how does it work? Ygen mainly have 4 steps. First, extract the influence fingerprint of the predicted result. Secondly, build a fingerprint database for all training samples. Of course, this database only needs to be established once, and it does not need to be established twice when using the Ygen in the future. Then, the fingerprint of the query code is used to search for the most similar fingerprint in the database. Finally, the retrieved training samples and their source paths are returned to the developers. In order to clearly describe the workflow of Ygen, we draw a workflow Ygen diagram. The user first input code to the code generator. When Ygen compares the influence fingerprints of the query code, when code generator generates the code, and searches the fingerprint database for the most fingerprints, so as to return their corresponding and code fragments to the user. On the other hand, the generated code by the code generator is returned to the user. We compared the default configuration of Ygen with several methods, and each method uses a different strategy to select the important neurons to compare the influence fingerprint. For example, random means to randomly select the neurons. Maximum and minimum means to select the neurons with maximum or minimum output values. And FFM means select the high values neurons from the feed-forward layer rather than self-rotation layer. As shown in the figure, the accuracy of top 10, top 5, and top 1 of Ygen in the 5 groups of experiments is much higher than other methods. This shows that the influence fingerprint compared by Ygen does a good job in encoding important information about the decision-making process during the code generation. It can efficiently to be used to find the training samples that share the similar decision logic with the query sample. As future work, we plan to improve the accuracy of retrieving relevant training examples by finding better influence fingerprints. We also plan to extend Ygen to support more and larger code generators based on other architectures. A large and more standard benchmark would be useful to better evaluate the different training examples retrieving methods. Moreover, it would be interesting and helpful to find the better quantitative metrics to measure the relationship between the training examples and the generated code, which can be used to evaluate the Ygen more comprehensively. Okay, the above all is our content and our paper and a little demo. If you're interested in our work and would like to know more about our Ygen, please check our paper or our GitHub. If you have any questions and suggestions, please feel free to contact us. Thank you for your watching. Next, I will demonstrate how Ygen works. Because of the COVID-19, I can't get out of the school to access my service. I can only demonstrate on my personal computer influence fingerprint for a known test data, and Ygen returns the most relevant 10 training data. These are local compared of training data and their influence fingerprints. And this is some of training data, and these are their influence fingerprints, also fingerprints, and these are local compares of test data and their influence fingerprints. This is test data's ID, and this is test data, and this is test data's fingerprint. And we take a test data, and it's already compared the influence fingerprint, and let's now find the most relevant training data. And you can see this is one of the test data, and it's influence fingerprint. This is influence fingerprint. And these are the IDs of the 10 most relevant training data compared by YGen, and the distance between them. And next, these are the 10 most relevant training data. Okay, that's all. Thank you for your watching.
Thank you very much. Thank you very much. And any questions? We have time to give a live discussion. Any question? For all participants, if you have got questions, you can just speak out or type your questions in the chat box. I'm not sure that whether there will be a postpone. Sometimes I cannot see the message.
Okay.
Any question? Oh, well, I have one question. So so it seems that the table 1 in your paper, so it seems that the result is for all of the code generators, right? Isn't like average or average value or something? It's just for all the generators that you have investigated, right?
Oh, yes.
And is there any difference between among different generators in terms of this value, the accuracy?
Can you please repeat the questions?
I mean, the table 1, you investigate the accuracy, it's top 1, top 5, top 10. But it seems that this data is for all of the code generators under investigation, right?
Yeah, yeah.
I mean, is there any difference between different generators, like the Codex or Copilot? Is there any difference when you use YGen on these different code generators? And have you ever observed any difference in terms of this accuracy?
Sorry, I don't compare with other code generators. I do this in the Code GPT.
Code GPT. So this table is only for Code GPT, not for all the generator.
Yeah, only for Code GPT, because the Copilot is based on GPT-3. It's too large, and I can't do experiments.
Okay. Do we have any question from the audience? If no, I have another question. So the evaluation measure, I mean the accuracy, seems to have an assumption that the recitations are the most influential samples to the generated code snippet, right? Because you use it as a golden answer, right? But how exactly can you can justify this assumption?
Yeah. We think the code generator generates code like the human brain make a decision logic.
Okay. Well, thank you for your answer. And if for all the audience, if you have any other question, you can type your question in the chat box, and our author should be able to view the question and give you answer. Okay, time's up. Let's shift to the next presentation. Yeah, Zheng Yuan, could you please share your screen?
Okay.
Okay, the third presentation will be given by Zheng Yuan, and the title is SE Box for DL, a modular software engineering toolbox for deep learning models. So please go ahead.
Okay, thank you. So hello everyone. I'm the speaker Wei Zheng Yuan from City University of Hong Kong. I'm going to present the SE Box for DL, a modular software engineering toolbox for deep learning models. And nowadays, we know that deep learning models is being applied in growing domains such as the image classification and the medical image diagnosis, and they are represented by the datasets as the task to learn. And deep learning models is the approach to the solution, which has diverse architectures, and even in some architectures, there are existing thousands of published models. And from our software engineering side, we have a bunch of techniques for maintenance, such as these evolutionary techniques and some testing techniques. So among these three components, there are too many combinations. And we think the difficulty in current combination is that the software engineering techniques are non-trivial, which means that it requires expert knowledge. So it is hard for the ordinary developers, for example, those who have no research training, and that it is hard to apply these SE techniques to their actual development. And also, implementation of these SE techniques would be difficult, tedious, and even time-consuming. But evaluation on repair models is necessary. But if the developer has a customized post-repair training and tuning code, and if he or she want to apply these SE techniques to many model and dataset combinations, that would be redundant. So if there is a toolbox which can assist us in applying these SE techniques, that would be much attractive. So from the existing workflow, we know that if we given a dataset, deep learning models, and SE techniques, whenever we want to apply SE techniques on model and dataset combination, we have to implement such a branch. And whenever there are many more combinations, there will be more branch. But we also know that as the time goes, there will be more such dataset models and SE techniques being proposed. So if you want to apply this or try to evaluate them, we have to implement once more branch. That would be much more redundant. So from our side, we propose SE Box for deep learning toolbox, which is a modular toolbox for users to design their pipeline. Firstly, our toolbox provide a web interface for the user to configure their tasks, where they can select their deep learning models they want to evaluate and datasets, and what kinds of the SE techniques they want to apply on these model and dataset combinations. When they pass this configuration to the backend servers, the servers will automatically fetch such model and datasets to the server itself and apply the SE techniques to that combination by the task runner, and the execution process and the task results will be feedback to the web interface so that the users can check the progress and watch the results in visualization mode. So this is what our toolbox provide. And there is one more thing we want to mention is that our toolbox is extendable by design, which means that when a user wants to implement his novel techniques in our toolbox, what he need to do is to implement such kind of technique in a function and then register his technique with a name and by our provided dispatcher, and so that the users can configure such technique on the web interface and apply it to the existing model and dataset combinations. So this is the extensible design. And next thing, I'm going to demonstrate our tools in a live mode. Our toolbox is open source on GitHub platform. You can access it with this link. And now I need to exit the PowerPoint. Let me see. I have already opened this toolbox on here. You can access it and give it a try quickly in Google Cloud Shell by just click these buttons. And here is some code for you to install the dependencies. Since the Google Cloud Shell do not equip with a GPU, so that I would like to demonstrate it in my own server. The first thing you need to do is to clone the repository and then install the dependencies. In my environment, I have already installed them, so that simply I just need to bootstrap the service by one command. And now I just need to copy the URL to the web browser. And this, you can see that we have opened our toolbox with a web interface. And on the left panel, we can select what kind of the task we need to configure. The most basic task is to evaluate existing model and dataset combinations. For example, the dataset, I think I would need to choose a small dataset to save time. And you can see that here is an official models from the PyTorch region, a lot of them. And even you can choose free-party models that is available on the internet. For example, here, if you simply search the CIFAR10 pre-trained models and create one of them, and since it's already on the GitHub, you can simply copy its repositioning and provide to our toolbox. And you can see that our toolbox will automatically fetch its models. Let me see which one I haven't tried. How about this one? And we can create whether to use the pre-train ways. And I think it's no more things to need to configure, and just click the run button. And our backend service will try to load the models. You can see that it will automatically fetch it from the GitHub, and as well as its ways, so that in loading the dataset, this may consume some time. And after that, there will be some progress bar to show the current progress. I think the server is being used by my classmates, so you can see that the most basic function is that it can help us to evaluate to current model and dataset combinations, and to apply some software engineer techniques, for example, to repair deep learning models. We can repair against the Gaussian noise. Similarly, we use these three-party models, and we can also change another one and apply the deep patch technique to do this. Since it require training process, and I just to demonstrate the process. How about I just run it, just one epoch to save some time, and just click to run, and you can see that the config that is sent to the backend, and similarly that it will load the data and model. And I think this task is really time consuming. After this process, with some progress bar finished, there will be a button here that can give you some give you the repair model ways for you to change, so that you can download that ways and put them on the server, and then use this local option, and so that you can configure another time, such as a fuzzing technique, to test that repaired models. But from my current process, I think it's really time consuming. Let me see. How about we watch the video? Sorry. And I think I can show you something which this is after a repair process, so that we can download that model ways to our PC and configure another task, for example, the mutation analysis, and something like this process is very similar. And going down, there will be some progress, and finally, that technique will scan every filters as the fuzzing process, and finally, let me see. It will give you a figure as a visualization to see what is the issue of each filter, how is the correlation to the accuracy or the performance. You can also download that mutants to your computer for further analysis. So I think this is all of my presentation, and see whether you have more questions. Yeah, thank you.
Thank you. Wonderful job. Thank you very much for the presentation. And any questions from the audience? Even if even though it's time consuming and we didn't really see the outcome, but we can try to use the tool, and we can access the link that you have shared, and try to play with the tool by ourselves, right?
Yeah.
Okay, any question? Well, when I see this title and when I see this tool, I come up with another similar tool, which is called Weka. Have you ever heard of that Weka? And it's like a benchmark infrastructure for data mining. And this toolbox is kind of similar to Weka. Of course, not as mature as Weka, but for me, it's kind of similar. And for me, from a user's perspective, I'm expecting the extensible extensible feature, which is very important because I just want to use this tool to quickly compare with other sort of methods and try my method in a very efficient way. And I think it's very interesting. I will try this later.
Thank you.
But maybe I missed some important thing. So do you have any like statistical analysis tools in your toolbox? I see your visualized outcome report.
Yes, the statistic is on our paper. More specifically, if you mention some detailed results that may in our another paper under review, so I think I cannot show it.
Okay, doesn't matter. No, I can access the web page and try by myself, and it's really interesting. And okay, thank you very much. And I think that's all for today's session. And we have 3 wonderful jobs. And if the audience have any questions, you can communicate with the authors directly. They have already left the email address, right? So thank you for your participants. And I think that's all for this session.
Ok. Okay, so bye.
Bye bye.